Good day! Today we presenting our study titled Fast Color Images Clustering for Real-Time Computer Vision and Artificial Intelligence Systems. Let's get into it. The development of innovative tools and modern technologies for pattern recognition is increasingly focused on the utilization of new models and algorithms of artificial intelligence, including clustering, artificial neural networks, and classification. However, challenges persist in achieving computational efficiency, particularly when applied in embedded systems. And traditional clustering algorithms face challenges in constructing clusters of arbitrary shape, leading to computational bottlenecks in modern computer vision algorithms. To solve these problems, in this work we propose a fast algorithm for constructing clusters of arbitrary shape. The parameterization of the algorithm makes it possible to effectively adapt in both for relatively powerful server system and relatively less powerful embedded systems. Unless otherwise stated, the input data is a color image in RGB format. Let's now explore some common algorithms in practice. Partitioning. Methods like k-means and k-medoids partition data based on proximity. Hierarchical. This approach builds cluster hierarchies through either merging or splitting data points. Density-based. Algorithms identify clusters based on dense regions in data space. These algorithms offer diverse strategies for clustering, each with its own set of strengths and limitations. In our methodology, we employ image downsampling techniques to reduce computational complexity while retaining essential image features. Downsampling involves reducing the resolution of the image by some sampling or averaging the neighboring pixels. This process allows for faster processing times and reduced memory requirements without significant loss of information. We optimize the partitioning grid in the RGBH space to reduce clustering complexity. Image preprocessing involves scanning and forming matrix to capture color distribution across pixels. Clustering is then performed using this matrix. By dividing the RGB space into enlarged cells and aggregating frequencies, we achieve computational efficiency. Further, analysis of frequency distribution aids in constructing clusters of arbitrary shape. This visualization allows us to observe how the enlarged cells in the RGB space partition contribute to reducing computational complexity while maintaining crucial image features. In many images, dominant objects have significantly higher color frequencies than other objects, appearing as distinct peaks on histograms. Analyzing all frequency distribution lines is unnecessary. To address this, we quantize frequencies into a predetermined number of levels, balancing computational complexity and quality. A non-linear quantization law is used to mitigate the influence of dominant objects. We propose flexible boundaries for frequency quantization levels. After determining model parameters, image preprocessing follows these steps. First, resize the image. Second, scan the image. A. Find cell frequencies on an enlarged grid in RGB space. B. Quantize frequencies. Use quantization levels instead of frequencies. The wavelet method offers a powerful approach to cluster formation, leveraging the concept of wavelets to analyze image data. This method proceeds through the following steps. A. Upon transitioning to a new level, cells are traversed starting with the highest density. New cluster forms if the centroid doesn't belong to any exciting cluster and no cluster formation is ongoing. B. A new cluster forms with the cell becoming its head. Neighboring cells in a 3 to 3 to 3 space are analyzed. All adjacent cells on the same layer are added to the cluster. C. Cluster formation continues until none of the input cells in it have any free neighboring cells located on the same layer. After scanning all cells, collision detection occurs between newly formed clusters and those on the layer above. If a cluster on the current layer collides with one on the layer above, they merge. Additionally, if two clusters share a neighbor on the previous layer, they merge into one. Here are the outcomes of our algorithm. We will now present an image showcasing the effectiveness and accuracy of our color clustering method. Let's take a look at the algorithm's performance and evaluate its efficiency. Our findings are summarized in the table presented. It outlines the size of cell, the number of colors detected, the processing time in seconds, and the clustering efficiency achieved. In result, we have introduced a fast clustering algorithm designated for images in the RGB color space. By employing preprocessing and adaptive quantization, we have effectively reduced computational complexity, thereby enabling nearly instantaneous clustering. The algorithm's effectiveness allows for its utilization in low-power embedded systems with parameters adjustable to specific tasks. Also, proficient in handling monochromatic elements, the algorithm may face challenges with diffused colors. That's all. Thank you for attention.